Hello, welcome back in this blockchain workshop. Today we are going to discuss in detail about few of the key concepts in blockchain. But before we start doing that, let's try to have a quick recap of what we had discussed yesterday. Yesterday we started our discussion and based most of our understanding on Bitcoin. So, what exactly is Bitcoin? Bitcoin is a virtual cryptocurrency or a virtual currency which any one of us can be part of, and any one of us can run the whole Bitcoin network without having a third party to run it. Right? So that's exactly what Bitcoin is. So today we'll see how a transaction actually take place in Bitcoin, how we can earn Bitcoins, how we can spend Bitcoins. We're going to discuss that in a step-by-step manner. We are also going to discuss about a couple of features that we have discussed about blockchain yesterday in slightly more detail. So the main features or the reason why blockchain is so important and why it is called the future of internet is because of its security features, the decentralization capabilities, the transparency that blockchain brings in, and also the immutability of data. Right, data once stored in a blockchain can never be removed or updated or changed. It can only be a new transaction can only refer to a previous transaction on a blockchain. Right. So there's a few things that we have discussed, and also to understand fundamentally what a blockchain is. It's nothing but a traditional database spread across multiple computers or nodes in a network, and few other added security features in terms of mutability, hashing, encryption, timestamping. So these are the few things that has been added on top of traditional databases, and they have been distributed across a network so that everyone gets a copy of the data, and whenever someone wants to query the data and use it, can have a request to the network and then get the data queried or received or updated, anything that they want to do with the data or the transaction, right? So that's basically blockchain is. So let's have a quick look on what we want to discuss today. So today we will discuss about where to use blockchain and where to not use blockchain. So what are the scenarios where blockchain makes sense and where are the scenarios where blockchain should not be used or avoided and we should go for a traditional database approach. We'll talk about the key concepts that we had already discussed yesterday, like a node in a blockchain, what a block is in a blockchain, how mining works, in a blockchain. So we'll discuss about those things. Later, we'll start our discussion around the security features in blockchain, why a blockchain, in blockchain the data is called immutable, and what Merkel tree is, and how a Merkel tree can help us to store data efficiently as well as in a secure manner. Right, we're going to discuss about that. Post that, we'll discuss how a transaction can take place in a simple blockchain network. And we build a simple blockchain network tomorrow. We're going to do this in hands-on, but today we're going to understand what are the steps that needs to be performed for a simple transaction to take place, or for data to be added into a block, and then that block to be added into a chain, form the blockchain. Right? We're going to understand that in a step-by-step manner, and then we'll discuss about a concept in blockchain which brings all these different nodes which are distributed geographically around different parts of different configurations of hardware and things like that. How do we bring all these nodes on the same page? So the type of algorithms or the mechanisms that are in place to do that is known as consensus. So we will discuss about different types of consensus algorithms that we have out there, which we are majorly using out there, and also we'll discuss which consensus algorithms are used by existing public networks like Bitcoin network or the Ethereum platform. What are the different types of consensus algorithms they are using, and what is the importance of consensus? We're going to discuss about that. and we'll also have a brief introduction on the Ethereum platform and smart contracts. So these are something very different from what Bitcoin is. So though we are starting our discussion on Bitcoin, we're going to do most of our hands-on sessions from tomorrow on the Ethereum platform. So we'll do those setups today and we'll have a brief introduction to Ethereum and a special tool that Ethereum gives us, which is known as the smart contract. We'll discuss in detail about that, and we'll end the session by discussing about a couple of architectures or use cases of blockchain, like how we did it yesterday. We'll discuss about how property records and blockchain has a major use case, especially in a country like India. Also, we'll talk about another use case, which is around digital credentials, how digital credentials can be stored in a blockchain and retrieved from it, what are the advantages it provides, what are the use cases that we have from an Indian context or in general from a software context, what are the use cases we have for digital credentials on a blockchain. So there's a few things that we're going to discuss today, and we'll also be doing a couple of simulations and hands-on things in between, a small snippets we'll do here and there, right? So before we start, let's try to understand what exactly the key features, one of the key things that we see about blockchain when we kind of Google for it or things like that. Blockchain talks about a distributed network or a decentralized technology, and also it talks about the need of trustlessness. There's no need of trust in a blockchain network, right? So there's a few things that blockchain always talks about, and if we remember the philosophy or the snippets that we have seen yesterday from Satoshi's paper that he published in 2008, the white paper, he clearly mentioned that Bitcoin, when he was building it, the philosophy behind that was to kind of build an electronic payment system which doesn't need a third party to do a transaction, right? So he was referring to the banking sector where individual A and individual B want to do a transaction in money on fiat currencies. They have to kind of send a request. Individual A has to send a request to the bank. Bank will debit that from A and then credit it to the B's account. And then, so both A and B has to kind of rely on the bank or depend on the bank to do the transaction in place, right? So Bitcoin was created with the motive that it has to be completely peer-to-peer and transaction should happen between A and B without needing a third party whom we have to trust with our money. So that was an electronic payment system on which Bitcoin came in picture, and it kind of gave an idea of what trustless systems looks like, or how transactions can happen without a mainstream banking scenario or a payment gateway scenario like Visa or MasterCard that we conventionally use, right? So Bitcoin kind of gave us a hint or an idea about that and kind of scaled fairly well in that space. So that's what how we started our discussion about trustlessness and decentralization and things like that. So today we'll discuss on those things again, but we'll try to see other utilities of these features of blockchain apart from the cryptocurrency part of it, where Bitcoin is one of the major use cases there, right? So we should again, I should reiterate and tell that Bitcoin and blockchain are not synonyms of each other. Bitcoin is just one of the use cases of blockchain, right? So yesterday we had discussed in brief about a couple of the use cases, like the use case of storing data in a blockchain kind of a network for IoT, the security that it brings in. We spoke about a microgrid system where the houses can share their energy resources over a blockchain dynamically and get paid for those sharing of resources. We also spoke a bit about supply chain management, how each point in which the data, the product moves in a supply chain, the data can be captured in a blockchain and then can be shown for better transparency to the customers or for internal operations. So there's a few things that we have already been discussing, right? So now let's try to understand in brief where we should use blockchain, what kind of scenarios, and where we should not use blockchain. So there are just a couple of scenarios where blockchain can be used or we should consider when we are building our products, when we're building our architectures. So we should keep in mind our architectures kind of fall in one or more of these kind of categories where blockchain should be used. And again, just to reiterate, though blockchain is a database which is shared across multiple computers and the compute power is shared and things like that. Blockchain as a technology is not designed to store heavy files. Blockchain is designed to do more of an timestamping architecture where we can kind of store authenticity of something into the network and then go out of the network and check for the actual data, right? That's what the philosophy on which the whole technology was created. But today, we do have implementations of blockchain networks where we can kind of store a couple of GBs of data without any problem, right? And there are certain different architectures and protocols that are being introduced apart from the blockchain technology or which are motivated from the blockchain technology. So if today we might do one example where we'll kind of try to host a static web application or a website onto a distributed network without paying for any cloud service, right? So there's a couple of hands-on things that we're going to do part of this workshop. So there we'll see how a static website which kind of has a lot of data-heavy files like images, fonts, JavaScripts, right? How can we store all those things in a decentralized manner, which is kind of adapted on a blockchain technology, right? We're going to discuss about those things. But now coming to a couple of key checklists that we should have when we're talking about a blockchain architecture. A blockchain architecture should come in picture majorly or primarily in scenarios where there's a need of a shared common database, right? Where the common database needs to be shared with multiple stakeholders, right? In a centralized architecture, database is kind of stored in a central server, and then the stakeholders who have certain permissions kind of query data out of that server, right? So in those kind of scenarios, using a blockchain and decentralizing the storage of the database makes more sense, and it also kind of brings a layer of adds a layer of security, and those are the primary features of blockchain, right? How the security is added and things like that. We're going to discuss about data immutability and other stuffs, Merkel trees and things like that. So that will have an idea of that. So that is one of the major spaces where whenever there is a requirement of a shared common database, we should kind of go ahead and think about implementing blockchain and part of our application development architectures. So there's another thing that we should remember is when parties which are what the kind of stakeholders of our applications or the architecture should not have conflicting incentives, right? So take an example of an enterprise scenario which has say X number of C-level executives, right, who are kind of decision makers in the company. And if you want to have a transparency, you as a CEO of the company wants to have a transparency on what are the kind of decisions they're making, what are the expenditures they're doing, and how the data is captured and things like that. If it is on a centralized architecture, anyone who is not working up to the mark or who is stuck within an organization can just go ahead and change that data and give you fake reports, right? But if you are including a blockchain kind of a architecture in your within your organization's data capturing mechanisms or performance assessments, you can kind of have a quick trail of all scenarios where data can be stored and captured and also have a good transparency of that. So transparency is another feature that blockchain brings in, right? So whenever we have scenarios where stakeholders might have conflicting incentives, we should think about a more transparent setups and which blockchain kind of helps. So another thing is where multiple parties are involved in writing to our database. That is same as the first one where there's a need of a shared common database. So there are a couple of other things that we are discussing here in terms of where blockchain should be used and where blockchain should not be used. There's one important thing is blockchains are distributed over a network which say suppose you have 100 nodes or 100 different individuals who are giving out their compute power to store your data files or do computations on top of your data files, right? And all these 100 nodes are spread across different geographies. It might be different parts of the country or in different countries altogether. And when we have networks which are connected in such a diverse geographical scenarios, so it is difficult to have heavy transactions on blockchain networks. Reason being, whenever a transaction takes place or a data operation takes place within a blockchain network, a copy of that needs to be sent across all the nodes in the network. So when you're talking about an example where we have 100 nodes in our network and a node 1 does a transaction, all the 100 nodes need to get a copy of that for the blockchain to exist or the network to run. And when you're doing data heavy operations or operations which needs high bandwidth consumption, the latency in the network will increase and transactions will not be instantaneous or it will take more time than what's required. So that's one of the reasons why blockchain networks or blockchain architectures should not be implemented in scenarios where your files are too heavy. The files that you're storing on the network are too heavy. We cannot use blockchains in those scenarios. A blockchain should be used only in scenarios where we're going to store only transactional information. Transactional information, good example can be how what Bitcoin does, right? When in a Bitcoin blockchain, the only data that the network stores is who is sending how much Bitcoin to whom and at what time it was sent. That's the only information. That's a simple couple of strings of data that is being stored. It is not storing any heavy files like videos or multimedia or text files and things like that. It's just storing a couple of strings within the network, and that's the reason why blockchain being so big, the size of the whole network is close to 300 GB plus. 300 odd GB is what the whole network size is today, right? So these are a few things that we have to keep in mind when we're talking about the use cases of blockchain or scenarios where, or the architectures where blockchain should be used. So one interesting thing to know is like yesterday, I think I mentioned the Bitcoin network. It can handle, on theoretically, it can handle 7 transactions per second. So there are only at any given point of time, there are only 7 people who can kind of transact Bitcoin currency on the network in theory. In practical, if you see, it is only 2 to 3 transactions that can happen per second. That's a very small amount of transactions. So one of the largest conventional payment gateways like Visa or MasterCard, they handle more than 1 lakh transactions per second. And on peak times like your New Year sales and Thanksgiving and Black Fridays and those kind of days, they kind of handle transaction volumes in the range of 2.5 lakh to 500,000 transactions per second, right? So that's the kind of latency that on a Bitcoin network which can handle only 2 to 3 transactions per second. So what happens in that scenario is if I want to use Bitcoin, which is a currency, to say go to a coffee shop and pay my coffee shop bill using Bitcoins. The problem that might come in picture is like though I have my coffee and I'll pay my bill using Bitcoins, the coffee shop owner will receive the payment only after a couple of hours because there can be only 2 to 3 transactions per second and there are thousands of people who are going to request a Bitcoin network for transactions, right? So that is one of the hindrances that people have in terms of using Bitcoin as a conventional spending method. But this is actually not a problem by itself. From the level 1, it looks like a problem. The level 2, the thing is, once a transaction is being initiated on a blockchain network, it cannot be reversed. So though I pay my coffee shop bill using Bitcoins and the coffee shop owner has not received the coins, it doesn't mean that I can reverse the transaction after I leave the coffee shop. I will not be able to do that. So he will eventually, the owner will eventually receive my payment. Only thing is we have to wait for a couple of hours to a couple of minutes, depends on the activity in the network. So this is a few scenarios where we should use a blockchain architecture. So a couple of major scenarios where blockchain architecture should not be used. One thing is in processes or systems where which involves kind of a confidential data. Reason being, blockchain is highly transparent. Along with being secure, it is also highly transparent. If you remember visiting the Etherscan website yesterday, or you can kind of visit the etherscan.io website now itself, and you can kind of see the Ethereum's online transaction platforms where you can kind of see each and every transaction that is happening on the Ethereum platform, or you can also go to blockchain.com and see all the live transactions that is happening on the Bitcoin platform. And that's how transparent the network is. So if you're dealing with confidential data, it is not preferable to go with a blockchain architecture. But if it's still required for you to kind of have security features and not a transparency feature, you can kind of go for added layer of encryption on your data and then store it on a blockchain. That's possible. But ideally, confidential data systems are not using blockchain as an implementation method. Another thing is processes that store a lot of static data, as we have discussed. Since blockchain is a decentralized network technology, each data that has been shared or created by one node needs to be replicated by all the nodes in the network. It will be difficult if for the node to run or to have a very high latency in the node if we use a lot of static data or big multimedia files and things like that, right? So that's one of the issues that we have in terms of handling static data in a decentralized network like blockchain. And one other important thing is the rules of transaction should not change very frequently if you are kind of trying to implement blockchain architectures as any system. The very reason being, yesterday we spoke about something known as Genesis block. The Genesis block is basically the first block that gets created into the blockchain, and ideally that is hard coded by the developer of the network, and he will put in rules and regulations on how transactions or how data should be stored in this particular network, how a new block can be created in the network, how the security layers work, how timestamping is done. So all those kind of things are kind of hard coded in the Genesis block. So now those rules cannot change for the rest of the network. So if you are dealing with a system where the rules in which you store your data or the rules or protocols that you use for your transactions kind of evolve over time, then it's not preferable to use a blockchain architecture in those scenarios. And the last one is use of external services to gather or store data. So though we have a type of blockchain that we have discussed yesterday called on-chain and off-chain, ideally pure blockchain scenarios should not be considered with an off-chain data storage. Off-chain data storage refers to storing data externally and having a reference to that in a blockchain. It does have certain use cases today out there. We're also going to discuss about few of those. Please mute yourself, everyone. Okay. So, though we are going to discuss about few use cases where off-chain data scenarios in blockchain can add certain values, but a pure blockchain network is not considered to be pure if it is storing data outside the network. Right? That's another reason where if you are dealing with a lot of data which cannot be stored within your network in terms of a blockchain, don't use blockchain in those scenarios. So this was just a quick brief about how or the scenarios where blockchain can be used or cannot be used. So next we'll talk about few of the key concepts that we have started discussing yesterday, and we'll take the discussion forward from there. So let's try to understand a few of the very fundamental things that a blockchain comprises of. It has something known as the record or the data or the transaction. Then there's a block which stores this data along with few other information. As we have discussed yesterday, it has something known as the output of the consensus algorithm. It will have a timestamp. It will also store hash of a previous block. That's how the chain is created, and then the chain, right? So the fundamentally we have three core things in a blockchain. It has a record of the data that needs to be stored, the block which is storing that data, and then the block needs to be added to a chain to create something that we are talking today as blockchain, right? So what exactly a node is? Let's try to understand that first. So as we have discussed, already a node is nothing but a hardware or a computer in a network which is running the required applications for a blockchain network to be functional. So, what a node comprises of, a node has a copy of the latest copy of the blockchain or latest copy of all the blocks that are available out there with the data in a serially stored manner. The node also does a couple of operations. One of the major things that node does, it helps in adding new blocks to the network. So the process of adding a new block to the network is known as mining that we have discussed yesterday. The node, in the process of adding new blocks to the network, nodes are also have multiple types. There can be something known as a full node. A full node is basically a scenario where everyone has a complete copy of the blockchain. The owner of the node kind of downloads the whole copy of the blockchain and keeps it. There are also scenarios where nodes can be created only for transactional verification. So there can be mining nodes, there can be transactional verification nodes, there also can be shallow nodes. We'll discuss about that a bit later. So these mining nodes, shallow nodes, or transactional nodes. The major difference being mining nodes are used for creating new blocks in the network. Transactional nodes are only used for validating transactions that is coming to the network, right? And the reward system on which the network works is very different for a mining node and a transactional node. Before we get into the things in terms of how a transaction takes place in a blockchain and things like that, let's try to understand what a block in a blockchain looks like, right? So ideally, a block consists of data or the transactional information. It consists of a hash. The hash is generated by computing the data, the timestamp, the previous hash, and things like that. And it also has the previous block's hash. So connecting blocks in a blockchain is made possible only by you having a reference to the previous block. So if my network starts for the first time, if we create a private blockchain network for the first time, so the first block that we create is a genesis block. So a genesis block, say, has an index 0 and stores any sample data that you want to store, and then we generate a hash using a hashing function. So in a Bitcoin scenario, the hashing function that is used is called SHA-256. So it's a SHA-2 algorithm that is being used for generating hashes in a Bitcoin scenario. And we do double hashing in Bitcoin. How does the double hashing work? We'll discuss about that in a while. So now when we try to create a second block in our blockchain, now the index of the second block will be 1, and the way we connect the second block to our first block is by adding the hash of the first block to the previous hash in the second block. So the hash of previous block will be the hash that is being generated in the genesis block that we have generated first. So the core components in the block wise, a block consists of a reference to the previous block. It also has an output known as nouns. Nouns stands for number which can only be used once, right? And nouns is generated by the consensus algorithm that the blockchain network is using. So we will discuss more about what proof of work is, how a nonce is generated for proof of work, for those things when we're talking about consensus. So proof of work, to give you brief info, it is a algorithm that Bitcoin network uses today for keeping all the network nodes on the same page in terms of the data that they have, and it also allows miners or the mining nodes in the network to add new blocks to the blockchain. And how is it done? It's basically a competition that each node in the network participates in, and they have to solve a complex mathematical problem to win the competition, and whichever node does it fastest kind of wins the competition and adds the next block in the blockchain and gets rewarded for it. And the reward will be a certain amount of bitcoins that they get, and that they can kind of go ahead and change to a fiat currency whenever they need from an exchange and things like that. Also, the nodes, apart from this, they also get paid for every transaction that they are adding into a block. So now one block consists of a reference to the previous block. It consists of a value or a number called nouns. So this number helps in creating the hash of the block. The nouns kind of helps in creating the hash of the block. We'll discuss about that in the simulation in a while. And then it also has a timestamp. Timestamp tells when this block was created. And then the last important thing is the data that is stored in the block. So the data or the transactions in a blockchain is stored with the help of a tree is known as a Merkel tree. So we'll discuss about Merkel tree in a while, and the reason why Merkel tree is important in terms of mutability of data, efficiency of the network. So we'll discuss about these things in a while. Before we move on to mining in blockchain, so the fundamental concept of mining is the ability to create new blocks in the network to make the chain longer and longer or the larger. And another thing about mining is to kind of create new coins and new cryptocurrencies in case of a Bitcoin network. So in a Bitcoin network, there can be only 21 million coins that can be created, and out of that close to 20 million coins have already been minted or mined. So mining kind of helps in creating those new coins in the network. Before we proceed with mining, just to have a quick recap about blocks, nodes, and the fundamental things. So we have discussed about the record of the data. Ideally, a blockchain can store any type of data theoretically, but practically, since it is a decentralized technology, we should not use static files inside a blockchain. And then comprising this record with this record of the data with the hash that has been generated for the block or the previous hash of the block, and timestamp and a noun's value, all these things when we combine together within a block, and then that particular block needs to be added to the blockchain. And Merkel tree is something that's helping us to kind of put multiple transactions into a block. So one important thing we should know is that we don't ask the miners or the nodes in the network to keep adding a new block for every transaction request that comes to the network. So one block in a blockchain, say suppose a Bitcoin blockchain, can comprise of multiple transactions into it, and all those transactions can be compiled together into one using a Merkle tree and then pushed into a block. So just to give you a quick understanding of how this looks, let's try to visit the Bitcoin blockchain transactions. So this is one of the explorers that we have seen yesterday also, which kind of lists out all the unconfirmed transactions in real time that has been sending requests to the Bitcoin network. And we have also seen the BitNodes visualization, which kind of shows us in real time how many Bitcoin nodes which are active now globally. Now, when we go to blockchain.com's Explorer and we come out of so you can just open any one of the transactions here. So here, this is one of the explorers that we are using for blocks. So the tabular information that we see, you can see something known as height, then we have something known as a hash, mine, like how much time back it was mined, and who was the miner, or which node mined it, and what was the size. The size of this block was close to 1.1 million bytes. And if you click on the height of the block, so this height is nothing but the index of the block. So this hash that is generated for each block is after combining all the data that we have here. So you can see there is something known as hash of the data. So if any one of you have difficulty in navigating to this explorer, you can just send your queries over chat. So you can just visit blockchain.com and go for Explorer and Bitcoin Explorer, and there click on any one of the block heights. And when you see the block heights information, we are just discussing about the information that we are seeing in the block heights. So when you see the core things that we have discussed about, the core components that a block has, it has something known as a hash. It also has a Merkel root that we have discussed about. It has something known as nonce and the timestamp. These are the four important things that the block has. Apart from this, the other information that you can see in the Explorer, so if you see, this is known as something that is showing us confirmations as 1. So I'll just refresh the page. So the confirmation is still showing 1. The Bitcoin network is slightly slow. It can handle only 2 to 3 transactions per second. So this confirmation stands for number of nodes in the network currently out of these 10,957 nodes which are active. So from here, the number of nodes which have kind of received a copy of this block. So there's only one confirmation. That means only the owner of the block has received it, others have not received it yet. So we have to kind of wait for a couple of minutes for it to get propagated. That's one of the reasons why heavy transactions or heavy files cannot be sent on the blockchain network. So this hash that we're seeing, this is computed by adding all this data that we see here, adding all this string data and giving it to a SHA-256 algorithm, and the output of that SHA-256 algorithm is the hash that we're seeing here. And this Merkel root hash that we see here, this is basically storing all the data. So these transactions that you see below, these are the number of transactions that are stored in this particular block. So you can see there's so many transactions that are being compiled together and then put into one block, which is having a height of 6,14,901. So this is the this is the blocks index. Height is nothing but the blocks index that we are showing. It is also showing you the number of transactions. So this particular block stores close to 2,000 transactions in it. So the understanding is public blockchains, when we're talking about Bitcoin or Ethereum, in those scenarios, every block will not be mined by the mining node for every transaction that request that comes to them. So they will kind of compile a couple of hundreds or thousands of transactions together, and then they will try to create a block and then put it in the network. The more the number of transactions they are able to squeeze in a block and create the next block in the network, better rewards they get. So let's just try to open another block height, so which has been slightly older. Let's say this one, which is the last one, which is around 2 hours old. So here, if you see, this is storing close to 2,600 transactions, where the previous one had stored 2,040 transactions, and here we can see there are 15 confirmations. It took 2 hours for 15 nodes to get a copy of this block out of 10,900 nodes which are active now, right? So that's how slow the Bitcoin blockchain is currently. and all the other information, if you see, they were all together. So the miner who mined this particular block into the existing blockchain got 12 and a half BTCs as a reward. So whereas the previous miner that we are exploring, so that particular miner also got 12 and a half BTC, but though they used a slightly less number of transactions, it might be also depending on the value of the transactions they're doing, right? So there might be two people who are sending 100 bitcoins to each other, there might be 20 people who are sending, say, one bitcoin to each other, right? So it also depends on the value of the bitcoins and things like that. So algorithm kind of does that. There's another important thing to understand from the block exploding data is the block difficulty that you can see here. So block difficulty kind of helps the consensus algorithm to generate the nouns value that we have here, and this nouns value helps us to create the final hash in our network. The final hash that is being created here. So that was a bit about exploring how a block looks like in a blockchain, especially in a Bitcoin blockchain that we were exploring currently. Next, we'll discuss about mining, how mining can be achieved in a blockchain, and what are the different ways mining happens. So, fundamentally, mining is nothing but adding new transactions within the network or adding a new block within the network, right? That's what mining is. So this is an ideal scenario that has been shown here, where a transaction is initiated by an individual and sends a request to the blockchain network, and then the blockchain network propagates that particular request to the nearest mining nodes and eventually to all the other mining nodes in the network. And then these nodes kind of start, depending on the difficulty value in the network, they kind of start creating a nonce value or a numerical value, which helps them to create a hash. Or is more of, to be more simpler to understand, it's kind of a mathematical problem that they have to solve to be able to get the new block into the blockchain, right? So all the miners in the node in the network who have received this transaction request, they kind of start competing with each other in terms of who solves the mathematical problem fastest, and then is able to put the block into the blockchain. So the transactions are added into the block, and then that particular block gets added into the chain. And then the final block, when it gets added to the chain, it waits for a couple of confirmation or a couple of nodes to get a copy of that, and the transaction gets completed. So in a Bitcoin scenario, when we were exploring blocks, we would have seen that the first block, which was only confirmed by one node, right? So though there are close to 11,000 nodes which are active, but for a transaction to be termed as valid and confirmed, the only 6 nodes have to confirm the transaction, and then it can be considered as a valid transaction. We'll discuss about that in a while, and we'll try to see that in some time. But this is how a simple mining operation takes place, where every individual, the network is built by individuals, and they have compute power that they have shared with the network, and they're helping the network to add new transactions and blocks into the network. Right? So this is a simple scenario where there's only one, each node has one miner and things like that. But today, the public blockchain networks like Bitcoin or Ethereum platforms, they have become so complex and the difficulty has increased so much. It is not possible for individuals to kind of create new bitcoins in the network. The amount of hardware resource required, amount of energy that is required for the nodes to run, to mine new blocks in the blockchain, those requirements have drastically increased, and for those reasons, today mining happens with a concept known as pooling. So what pooling basically talks about is so all the miners who are interested in being part of a particular blockchain network. So let's take an example of the Bitcoin network. So they will kind of come together and create a pool, and that pool will have all the compute resources that they want to share. So there are say 100 people who are interested in mining together, and they all want to give say a part of their CPU for the compute resources. So there will be 100 into the X percentage of CPU that they want to give. So that will become a much larger and much powerful way of mining than an individual who want to mine separately, because it's a competition at the end of the day. So everyone will be competing to solve a mathematical problem to kind of create the next block in the blockchain, right? So whoever does it fastest kind of wins the race. So if a pool of miners will always be able to do it faster because they're like more compute power they have, and the financial burden will not be on one particular individual to kind of pay for the energy resources or pay for the compute power. So there can be hundreds of these interested, like-minded people can come together, share the cost required for mining the network, mining blocks in the network, and then also share the reward depending on the percentage that they have given to the network, right? So this is how mining happens in a pool kind of a scenario. So the flow remains exactly same. Transaction is initiated by an individual, transaction gets broadcasted within the network. The nodes or the mining pools in this scenario who receives these transaction requests kind of starts solving the mathematical problem to be able to create the next block in the blockchain. And then once the block is created and sent into the blockchain, it has to be propagated or sent across the whole network. That if I am part of a pool and the pool has to kind of send that new block to rest of the network, telling them that this particular new block has been created by me and I was the fastest to do that. So the moment six or more nodes get a copy of that block and accepts that, the transaction is termed as completed. So this is how a simple mining operation looks like. So mining can be done either as an individual, mining can also be done in a group, which is more feasible in terms of the economics around it, because the difficulty of the networks are increasing every day, and it needs a lot of resources in terms of compute power as well as the energy resources that is required for the compute to run to mine new blocks into the blockchain, right? So this is about mining. Next, we are going to talk about data immutability and Merkel trees. So, any questions till now, you can shoot them over the chat window and we can discuss them as we go along in the session. Fine. Let's start with the concept of data immutability in blockchain. So, blockchains are termed as secured, transparent, and decentralized. So, I think by now we have an understanding of what decentralization is. It's nothing but storing the network copy, the data copy of the network across multiple computers or multiple nodes in a network. Transparency, we have seen the blockchain explorer some time back, where we kind of saw how each block looks like, what are the transactions that each block comprises of, and things like that. So next, and one of the most important concepts that blockchain brings in picture is the immutable nature of data or transactions that goes within the network. So, data, as we have discussed already in a blockchain scenario, once it is entered into the network, cannot be updated or removed or deleted, right? So, how is that possible? And if anyone tries to do that, how can we easily trace them, or we can remove them from the network, or we can kind of term them as invalid nodes in the network, right? How do we do that? If someone tries to do the manipulation of data, how we can easily trace them if we're trying to understand that. This is one part that we're going to talk about today. Another thing that we're going to discuss in this subsection is about Merkel trees. So Merkel tree is one of the core concepts that is enabling data immutability. It is also enabling efficiency in the whole network. And how the efficiency is enabled by Merkel tree, we'll talk about that. And what is the major use case of Merkel tree? We're going to discuss about that also. So the concepts of Merkel tree and the other things that we will be discussing in the block in terms of hashing of data, proof of work. So these are the concepts which existed much before blockchain existed, right? So these are the concepts that Satoshi took help from in his white paper when he was publishing in 2008 and kind of created blockchain, right? So these are the technologies which are not new or which are not something that is being built because of blockchain. These technologies existed much before blockchain started. Now let's try to understand what we understand. What is our understanding when we talk about immutability of data? So right, this is how Anthony defines immutable nature in blockchain. So when people say that blockchains are immutable, they don't mean that the data can't be changed. They mean it is extremely hard to change without collusion. So if you try, it's extremely easy to detect the attempt, right? That's what we're going to understand now. So it is not very difficult to change data into a blockchain because every node has a copy of the data. They can kind of tamper with the data and things like that. But if they try to do that, they can never be benefited from that. And how is that being made possible, and how to trace those people who are going to change data into the network? Let's try to understand that. That's where Merkle trees concept comes in place. So a Merkle tree is basically a binary tree which helps in storing large amounts of data hashes as one hash. And it is kind of a scenario where we can store multiple data. Say suppose the block that we were exploring some time back, which had say close to 2000 transactions into it, right? And we had seen a hash string in the Merkle attribute value. So that particular, so I'll just try to share that screen again. So here if you see the Merkle root that we have here. So the Merkle root, the hash that is generated, this one hash is enough for us to validate all these 2000 transactions that we are seeing here. So all these 2000 transactions need not be stored separately within the block. If you want to just validate these transactions, only this one hash is enough. And how is that made possible? We'll try to understand that now in terms of a quick visualization of how a Merkle tree looks like. This is how a simple Merkel tree looks like. So we have a small part of a blockchain, let's say, which has say, up to 12 blocks. So we are showing three blocks out of the blockchain, the last three blocks of the chain, which is the block number 10, 11, and 12. And this particular block, if you see, it consists of something known as the previous hash, the timestamp, the transaction root, and the nouns. So each block is connected to each other using the previous hash of the block. So block number 11 is connected to block number 10 using the hash of block number 10 in the previous hash field. And then block number 12 is connected to block number 11 using the hash that is being generated by block number 11 and storing previous hash here, right? So now, what does this transaction root talk about? This transaction root is nothing but the Merkel tree's transaction. This is what stores all the data that is coming to our block. Rest of the things are add-on fields that we have to a block. All the data that we're talking about in a blockchain, that is the transaction root is storing it. And how that is being done? So we are taking an example, say our particular block is storing 4 transactions or 4 data feeds from index 0 to index 3. So we convert all of them into a hash using a SHA-2 hash functions, and then these hashes are clubbed together in a binary tree fashion, and we get a hash. So hash 0, hash 1, hash 2, hash 3 are the hashes that is being generated for transactions 0 to 3. And then hash 01 is generated as a combined hash of the transactional hashes of transaction 0 and 1, similarly for hash 2, 3. And then the final root will kind of store a hash of hash 01 and hash 02. So the final hash that is going to be stored will be hash 0123, right? So that's going to be the final hash that is going to be stored into the transaction root. This is how a Merkel tree works. So Merkel tree is a binary tree structure which helps us to store hashes of our transactions, but also it stores only once. So now in a normal scenario, if you want to create a block for each transaction, then each block's hash size will be 256 bits, because SHA-256 stores the hash in a 256-bit memory. So for 4 transactions, it is going to be 256 into 4, that is 1024 bits that is going to be stored in an ideal scenario. But what Merkel tree does, Merkel tree combines all these hashes in a tree structure to one hash. So instead of storing 256 into 4, it stores only one 256-bit hash in the root. So this is how the efficiency of the network increases in a blockchain scenario. So the efficiency is being increased by reducing the size of the block, and that is being reduced by combining all these transactions into one hash, right? So that has been made possible because of Merkel tree. So that is one of the use cases of Merkel. So Merkel tree helps us to kind of make our blockchains efficient by storing less. But now the question that arises, how we can validate the authenticity of transaction 0 to transaction 3 just with one hash. So the algorithm is designed in a way that if we pass the hash 0 as a comparison for this, it will be able to give us a binary it will be able to give us a Boolean output telling that the hash 0 exists in transaction root or no, without even having a reference of that. So the algorithm is designed in a way that Merkel helps in achieving that part of validation, right? So this is one of the use cases of Merkel that we have out there. Now we'll talk about how the immutable nature of data works in blockchain. So security wise, immutability is one of the key things. And efficiency wise, how Merkel is being using, we have just seen how it reduces the storage of data to this. Ideally, the block explorer that we were seeing on blockchain.com, which had like 2000 transactions, so size of the block would have been 2000 into 256-bit hashes for the Merkel or the transactional hashes, but it stores only one 256-bit hash. right? So that's how Merkel increases efficiency. Now we'll talk about the immutable nature of data, how immutability can be achieved in blockchain. So again, we'll take a small snippet of our existing blockchain. Let's say we have a simple chain which is having up to 12 blocks. We have taken the last 3 blocks in the blockchain. So here, again, the same things. We are storing the previous hash for connecting the blocks. We have a timestamp for the block. We have a nouns. Nouns, as we have discussed earlier, is something that helps us to generate the final hash of the block. And then we have the Merkle root or the hash of the transactions, right? So that we are taking an example where we are doing 4 transactions from transaction A to A, B, C, and D. The hash of A is generated, hash of B is generated similarly for C and D. Then these hashes are combined together, and the final hash that we have got in the root, that is the hash ABCD. That is the Merkel tree's hash that is being generated, right? So this is our blockchain that is being done, and this is how the transactions are being stored here. Now, let's talk about a scenario where someone who is running a node in our network tries to manipulate with this data. Say someone in the network wants to change one of the transactions in the network. So the changes that he can do, maybe say I want to send 2 bitcoins to someone on the other side of the network, and I'm using the network to kind of do my transactions. The node who is receiving my transaction maybe send only 1 bitcoin instead of 2 to the receiving party and keep 1 for himself, right? He can easily manipulate that transaction. So how this manipulation is not possible in a blockchain scenario, and even if that happens, how is it easy to navigate and see that particular node who is doing it? Let's try to understand that using the immutability feature and Merkle tree's use case. So, as we have discussed earlier, we are trying to manipulate one of the transactions. Let's say we are manipulating transaction A. The moment we manipulate transaction A, the hash, so the now the new transaction is known as A dash. So the hash of A dash will be different from hash of A that we had in the previous node. So previous node we had transaction A. The moment we change the values of our transaction, the hash will change automatically. So hashing is done using SHA-256 algorithms, and then these hashes are stored in the hash AB. So that also will change to hash A dash B, and then hash A dash BCD, right? So this is the final hash is also different now. The moment this hash changes, this will not match with the previous hash that was stored in block number 12. And when this case arises, this blockchain breaks. So now everyone in the node will have a blockchain with up to 12 blocks, and this particular individual node who has tried to manipulate a transaction will have a blockchain only got 11 blocks. And the fundamental rule, as it says, the node which has the longest chain survives in the network. Longest, and the majority of them should have the longest chain, right? So that's what survives the networks. Now, since this node has only 11 blocks in the blockchain copy that the node consists of, this will not be able to perform any other transaction for the network as long as they don't get a new copy of the blockchain with the same data that was already available till block number 12. This is what immutability of data is all about. So when we talk about data immutability and Merkle trees, so anyone can change data in a blockchain, but the moment they try changing the data, it kind of breaks the chain, and the moment the chain is broken, they have to wait till they get the copy of the actual chain to do any valid transactions in the network, right? So that's what Merkle is all about. So next we are going to talk about how we go ahead and do a transaction, a simple transaction in a blockchain, and next post that we'll discuss about a Bitcoin transaction, how from individual A to individual B you can kind of send a certain number of Bitcoins, and what are the different steps that's involved in it. So most of it fundamentally we have already discussed till now in terms of how mining works, how a block is being added to the blockchain, what are the different components of a block are. So there's a few things that we have already discussed till now. So next, let's try to quickly understand how a simple transaction takes place in a blockchain, right? So this is a brief infographic in terms of how something like that might happen. Someone sends a request for a transaction. It is being sent out to the network. So these requests can be sent in each other Bitcoin blockchain. The request will be sent by a wallet. So what wallets are, we're going to discuss next. So generally this wallet is an application which is storing our coins, and then these coins are kind of shared with each other using the wallet address. The transaction is very similar to how we do a Paytm transaction or a UPI or a Google Pay transaction. The user experience is exactly same as that, but the behind the scenes operations of these transactions are very different. So when the moment the wallet kind of sends a request, the network will receive the request, the network will validate the request, and then the miners in the network will kind of create a new block and add it to the blockchain. And a couple of nodes in the network kind of have to confirm the transaction, and the transaction will be termed as complete. So this we have already discussed earlier. Now let's try to understand from a cryptocurrency standpoint, what are the different things that we need to have as an individual to do transactions. One, the user who is using a cryptocurrency will have to have a wallet, and then they can kind of use the wallet to send or receive cryptocurrencies or manage the currencies that they have, right? So in our case, it can be either Ethereum or Bitcoin that we're going to work on now. And now the wallet that we're talking about, wallet kind of creates two security keys for us. So one of them is a private key, one of them is a public key. So private key is something that we're going to use whenever we are going to send or do any transaction and we're spending our currencies. We're going to use the private key to kind of sign those transactions, to kind of tell that we are giving permission to do that. And public key is something that is going to be used for receiving coins or receiving transactions, right? So that's about the wallet, and then the node is something that we've already discussed. Node is nothing but all the networks and the computers that's going to be connected to each other. We're going to share compute power, do validation, create new blocks in the blockchain, right? So that is something that's the node's work is. Now, how does a simple Bitcoin transaction look like? So we're talking a lot about Bitcoin. We have seen how the explorer of Bitcoin looks like, the block explorer, how the data is stored in blocks. We've also seen the Genesis block of Bitcoin earlier yesterday, the one that was built by Satoshi, and all the rules which are governing the network till date since 2008 is the same, right? So Bitcoin is kind of a legacy blockchain technology today. We have much faster networks, we have much efficient networks out there, but still we are using Bitcoin because it helps us to kind of get the fundamentals right before we move on to efficient networks out there. So before we talk about a simple Bitcoin transaction, let's try to understand how a Bitcoin basically look like, right? So Bitcoin is nothing but a set of keys, which is a public key or a private key. So as you can see here, it is using an RSA algorithm to generate these keys, right? So which is very difficult for any individual to kind of remember. So for that reason, we use wallets. So these wallets can be soft wallets, it can be hard wallets, it can also be something known as paper wallets. So what is the importance of wallet is, if say I want to get some purchase some bitcoins from an exchange and store them and maybe use them after some time. So now for storing those bitcoins, I just need to remember my private key. So as long as I have an understanding of my private key, like I can remember my private key properly, I can have control over my coins in the Bitcoin network. If I forget my private key or if I leak my private key to someone else, they will get control over the coins that I have, right? So a wallet kind of helps us to do that. Wallet kind of A soft wallet like Jax, JAXX. So Jax is one of the most commonly used wallets that we use out there today, which kind of keeps a copy of our private key secure, which we can just use a mobile application to do our transactions as smoothly as how we do a Google Pay transaction, right? So soft wallets are like that. Hard wallets are a scenario that are kind of USB devices which kind of store this token within a hardware, and we can use that hardware token anytime we want to do a transaction. So hard wallets are generally used for that. And then comes the paper wallet. Paper wallet is the most cheapest and it can be considered as one of the safest way of storing. So in a soft wallet, the scenario can be that your phone gets corrupted, you might lose your wallet. Your hard wallet is a scenario where you say you lose your hardware device which is storing your token, you lose all your currency. The paper wallet is a scenario where you can just take a printout of this private key in a paper and store it somewhere safe, right? Put it in a file and keep it somewhere. Because the junk string, no one can actually understand what the string refers to and things like that, right? So paper wallets is basically that. So paper wallet is used by a lot of people who are actively investing in cryptos globally. So they do use paper wallets actively for those reasons. Now we'll try to see a quick understanding of how a simple transaction looks like in a Bitcoin network. So by now, the couple of infographics and the couple of discussions that we have been having, you'll see similarity in a lot of these transactional workflows. Ideally, a transaction starts with a request, then it is propagated to the network. Network kind of validates the transaction, puts it into a block, and then kind of sends that whole block to the rest of the network, and transaction is termed complete. So it is kind of similar in a Bitcoin's scenario also. Now let's try to understand what's happening in this particular infographics. Here, so we have two individuals, Rob and Laura, and Rob is kind of trying to send say zero point 0.3 BTC. BTC stands, it's a unit for Bitcoin. So zero point 0.3 Bitcoins is being sent by Rob to Laura. So what he does now, both Rob and Laura, the first thing that they have to do is they have to go ahead and create a Bitcoin wallet. So they can either use a paper wallet, they can use a hardware wallet like a token, USB token, or they can use a Android app or an iOS app to kind of create a wallet, right? The moment they create a wallet individually, both of them will get a private key as well as a public key. So now Rob is sending the bitcoins to Laura. So Rob will need access to the public key of Laura. It can be a QR code that Laura sends, which Rob can kind of scan, enter the zero point 0.3 BTC that he's planning to send for transfer, and then those that particular transaction that Rob has initiated needs to be signed by the wallet using the private key. So that's what is happening here. So the transaction will kind of get signed by the wallet using the private key of Rob. The Rob's private key is going to be used for signing the transaction. And once the transaction is signed, it is going to be sent to rest of the blockchain network. So now Rob and Laura, though they are doing transactions in Bitcoin, they are not nodes in the network and they don't have to be part of the network to do a transaction. So owning a wallet doesn't mean that you are part of the actual Bitcoin network. Wallets can use APIs to connect to the network and do transactions for you. That's the exactly same thing happening. So here both Rob and Laura are not nodes in the Bitcoin network, Bitcoin blockchain network. They are just using the wallet to do transactions with each other. So now the network will validate the transaction that Rob is sending. So one of the things that network is going to do first is it's going to check if the amount of Bitcoin that Rob is trying to send is already existing in his wallet or not. If that much amount of coin is already available with Rob or not. If it is not available, the transaction will get declined. So it might be a scenario that Rob is trying to send zero point 0.3 BTC, but he might not have any Bitcoin at all, right? So the smallest unit of a Bitcoin is known as Satoshi, and Bitcoin can go up to 8 decimal points, right? So you can always share a fraction of the currency. You don't have to kind of share the currency as a whole. So he's trying to share zero point 0.3 BTC here. So now assuming that the network validates the transaction and the transaction is kind of added, sent to miners. Now miners will compete with each other in terms of sending in terms of adding the new block in the blockchain, right? And now, the moment one of the miners is successfully able to put the transaction in with a bunch of other transactions, create a Merkel Tree hash, and create the new block and put it into the blockchain, he will send the new block to rest of the people in the network, rest of the nodes in the network ideally. And moment 6 nodes accepts that new block, Laura will receive a transactional confirmation. She will receive a confirmation that she has received zero point 0.3 BTC. Now, this whole process will, in a normal scenario, when Bitcoin initially started gaining momentum as early as 2012, 13, it would have been done instantaneously because there were very few people on the network. There were very few people who were using Bitcoins. Cost of a Bitcoin was close to $1.80 back then. Today it has crossed $5,000 plus. Right? Today there are many people on the network. Today there's a lot of transactions happening. So ideally, a request like this might take a good 45 minutes, 45 plus minutes, right? Now, apart from this zero point 0.3 BTC that Rob is trying to send, right? He also has to add a small fee along with this. That will be a transaction fee, and that will be act as a reward for the miners, for the transactional nodes in the network. The transaction fee is also important because it is not compulsory that everyone who is sending money on the Bitcoin network need to add a transaction fee. But the algorithms are designed in a way that if you have a transaction fee, the higher your transaction fee, faster will be your transaction. So if Rob adds slightly more transactional fee, the transaction might get completed within 30 minutes because the nodes who are receiving these transaction requests will only mine and confirm transactions which are paying them more, right? Which are paying them more transactional fee. That's how the system is designed. So if you don't add any transactional fee, your request will not be rejected. It might still, the transaction request might still be live, but it might take, say, 6 months for the transaction to get completed, right? Or it might never get completed depending on the node who is receiving it. If the person who's running the node isn't like a really good mood to do a kind gesture, he might do a transaction for free. But ideally, no one will do that. So this is how a simple Bitcoin transaction looks like. This is how two individuals can transact money using wallets and things like that. So next, post this, we want to discuss about consensus and what are the different types of consensus algorithms we have out there and things like that. So before we start discussing about consensus, we'll do a small activity. I think in the pre-workshop guide, we had requested you to add a plugin to your browser, which is the MetaMask wallet, which can be added to your Firefox or your Chrome browser. So what we're going to do now is like we'll quickly set up our MetaMask and we'll create our wallet. MetaMask is nothing but a Ethereum wallet. So we'll set up the wallet and then we'll try to get some ethers into our wallet for all the practical applications that we're going to do from today and tomorrow, right? So let's start doing that. So what we can do, we can visit our browser. So I have not set up my MetaMask yet, so I'll be doing it right here. So if you have installed MetaMask already, you will see a small fox icon which gets added to your browser. If you have not done it, then please visit metamask.io and you can add the right extension that's required for your browser. If if you have any issues in setting up MetaMask, please feel free to send your queries over chat window. We will try to fix this. All of us need to have a MetaMask wallet set up with some free ethers in it before we start doing our practical sessions today and tomorrow, right? So how do we, once you have visited metamask.io and added the extension to your browser, it will be added in the top right. You can see a small icon. When you click on that, it kind of asks you to set up a new wallet. So I'm going to go ahead and create a sample wallet here. So we'll click on get started. It will ask us two options. If we already have a wallet and we want to import it, or we want to create a new wallet. So if you see closely here, it's giving the first option. I already have a seed phrase, right? So this is very important. The next step when we start creating our wallet, we are going to get a seed phrase, and we should kind of copy and store that somewhere separately, safe, because whatever ethers that we're going to get in our wallet now for our training purpose, if tomorrow your system crashes or your browser gets corrupted, you lose your MetaMask wallet, you will need that particular seed phrase. This is like a passphrase, password, which you will need that to kind of fetch your ethers back from the MetaMask wallet. Now I'll go ahead and set up the wallet. I'll click on create wallet. I'll agree to the conditions. It is asking me for a passphrase up to 8 characters. So I'm entering my passphrase and we'll go ahead and create the wallet. So now, the moment we go to the next step, you can see it is giving us something known as a secret backup passphrase. So if I click here, this is a passphrase that is being generated for me. So a passphrase will also get generated for you. So just copy this and keep it safe somewhere. I've just copied and just written a simple file and I'll save it. And then we'll go next. So now it will ask you to confirm the secret passphrase that was generated in the previous step, right? So this is the reason why you need to copy your passphrase and keep it separately, because in the same order you have to enter the passphrase again. So this, I'll just try quickly entering the passphrase that I have got here. Next will confirm, and it will give you a congratulations all set option, and your final wallet is going to be created. So if all of us are able to reach till this stage where you're able to create a wallet which has say zero ethers in it, please send a thumbs up in the chat window so that we can proceed to the next steps after this. So once we have set up our MetaMask wallet with zero ethers, next what we're going to do is like we're going to get some ethers into the wallet. So by default, if you see on the top right here, we have the main Ethereum network that has been selected. Just choose a drop down and change it to Rinkaby. Rinkaby testnet is being chosen, and here also you can see the ether count will be shown as zero only. So next, just copy your wallet address that is being shown here. Just copy the wallet address from here, and on a new tab, we're going to visit the Rinkaby pocket. I've shared the link in the chat window. So the moment you visit the interview pocket, it is going to ask you to paste a social network URL containing your Ethereum address. So now, how Rinkaby works? Rinkaby is basically a test network. It is not the main blockchain network on which the real transactions are happening. It is a test network, and it uses a different type of a consensus algorithm. So, how this type of consensus algorithm works we're going to discuss a bit later. First, I'll try to demonstrate and see how we can get some free ethers. So the steps that you have to do now is like just copy this particular wallet address that you have on your MetaMask and go to any one of your social media accounts that you have, Twitter or Facebook, and just paste that particular address and tweet it or just create a post for it just for a couple of seconds because we need that post URL to be pasted here to get our free ethers, and then you can delete the post after a couple of minutes once this is done. So copy the wallet address, paste it as is in your Facebook or Twitter post. Copy the post URL and paste it here and select any one of these three options. Ideally, you can select the largest option, which is 18 ethers for 3 days. Select that, it will automatically create a send those particular wallets to your send those particular ethers to your wallet, right? We'll wait for a couple of minutes till all of us are able to do that. Others who are not able to do this, feel free to send your issues and queries on the chat window. We can get them fixed before we proceed next, because we will be needing these ethers in our wallet for rest of the practical sessions that we're going to do. You should continue. Yeah. So I think couple of us are able to get the ethers funded to our wallet. So I can see in the poll, eight of us have got the wallet address posted on social media and then received some coins. So all eight of you have received your ethers in your MetaMask wallet. Can you send a yes in the chat so we'll understand if all of us have received the coins or not? Okay, so next, once our MetaMask is set up and we have got some coins in it, others who are facing issues, feel free to send your queries over the chat or try to set it up before tomorrow because tomorrow we're going to use the same wallet and the coins in it for all our practical implementations that will be required there. So now we'll talk a bit about consensus. We'll discuss about what consensus is, what are the different types of algorithms we have, and what exactly we did just now with Rinkaby, the Pocket Rinkaby Pocket, where you have to use your social media account to get coins credited to your wallet, right? So let's try to discuss about that. So, as we had discussed yesterday, also consensus is basically a mechanism for getting all the blockchain nodes on the same page, or all of them to get the exact same copy of the blockchain that is present in the network, right? So, consensus is talking more about those things. Uh, Getting okay, someone is getting invalid Facebook post URL. Please share your URL. So, continuing the discussion on consensus is basically used for that, and how consensus is used in a couple of the practical blockchain networks that we have out there, mostly the public networks that we have out there. We're going to discuss about it now. So, first, we'll talk about the proof of work consensus. So, the proof of work consensus is typically the consensus algorithm which is used in Bitcoin networks and also in the Ethereum platform that we're going to talk about tomorrow. So, proof of work consensus talks more about doing some sort of work before the node is eligible to add a new block to the network, right? So that's what proof of work is talking about. So in Bitcoin scenario, the thing that is happening is that any miner who wants to create a new block in the blockchain network, he has to solve a particular mathematical problem to compute a nonce value. Nonce is nothing but a number which can be used only once, and that particular value is used for creating the transactional hash in the network. So now how Bitcoin system work, how the nonce value is created, and how the difficulty is affected is based on the hash that is being created for a transaction needs to start with a certain number of zeros, right? Let's try to go to the block explorer once again and check any one of the blocks that we have. I'll go to the Bitcoin explorer and I'll click on any one of the blocks height. So here if you see the block hash that we have here, it starts with a certain number of zeros, right? For to achieve these number of zeros, we need to add a certain number to our data for the hash function to generate this. So that particular number that we add to our data to create a hash like this is known as nonce. So we're going to see this in practical tomorrow when we write some scripts and code to kind of generate these hashes. So if we will be seeing tomorrow that the more number of zeros we add, the more number of compute time it increases, right? So that's what happens. So nonce is basically a number which is used only once per block, which helps us to generate the final hash of the block with a certain number of zeros that is being specified. So that is one of the major things that proof of work talks about. You have to kind of solve this mathematical problem of finding a nonce value which can say generate a hash which starts with 7 zeros in front of it. So proof of work is basically doing that. So proof of work has its own advantages and disadvantages. One of the advantage of proof of work is since every node in the system is doing some sort of activities to kind of take the next step in terms of putting a block in the network and things like that. It kind of helps in tackling the DDoS attack or denial of service attack where no one can just spam the network and things like that. Everyone has to contribute in terms of resources, compute power, energy to be part of the network. It has an advantage in that scenario, but also on the same hand, it has a disadvantage. Disadvantage is that proof of work needs a lot of resources. It is not eco-friendly in nature. So today, mining one block in a Bitcoin network is close to Denmark's energy consumption for 1 week, right? So that's the huge amount of resources that has been used. So that led to development of different other consensus algorithms out there, and one of those which is gaining momentum now, which is known as proof of stake. So proof of stake is a consensus algorithm where instead of you solving a particular mathematical problem to put a new block into the blockchain, this will give more opportunity to individuals who have more stake or more hold of the cryptocurrency in that network. Say suppose we're talking about Ethereum network or say Bitcoin network. Currently, it moves from proof of work to proof of stake algorithm. Scenario that will happen here is whoever has more number of bitcoins will get the opportunity first to create the new block in the blockchain. So in this way, it will not depend on the compute power, resources, energy, and things like that. So the problem that might happen here is the person who is having more and more bitcoins will always control the network. But the thing is, the modifications of proof of stake tells that person who wants to be a decision maker in the network has to lock in a certain amount of his funds within the network. He will not be able to use that fund unless and until he stops being a regulator. And if he does any wrong verification of transactions and regulations within a network, he will lose all his stake or all his cryptocurrencies that he has locked in the network, right? So proof of stake basically talks about those things. Then we have another interesting consensus algorithm which is built at Intel, and it is part of an open source private enterprise blockchain framework called Hyperledger Sawtooth. This is known as POET. So POET stands for proof of elapsed time. So this is a very different type of consensus algorithm. Here, the opportunity to create a new block into the blockchain doesn't depend on amount of money that you hold in the network or amount of compute resources that you have. It depends completely on a random generator, which randomly creates wait time for all the nodes in the network. And whichever node gets the least wait time will have the first opportunity to create the block. Right? So there are 5 nodes in a blockchain network, and all of those nodes are getting a random wait time. So one node gets 2 seconds, another gets 3 seconds, Some gets 1 second, some gets 10 seconds, right? So the least wait time is a 1 second node which will have the opportunity to create the first opportunity to create the block in the blockchain. If they fail to do so, then it will go to the next least wait time. So in this way, it is much more efficient, it is much more faster, and today most of the enterprise blockchains are moving towards OIT consensus algorithm. The last algorithm that we will discuss today is proof of authority. Proof of authority is a way of telling the network that you have a certain authorities to get or to be part of the network or do a certain transaction in the network. So one example is something that we did recently in MetaMask, where you kind of pasted your Facebook post URL or Twitter URL, and you got those coins to your wallet, right? What exactly happened there? The wallet address that you tweeted or you posted on your Facebook wall that got passed by the pocket of thingQbator, and they credited those cryptocurrencies or ethers, we call it in Ethereum scenario, to your wallet, right? So proof of authority is the operational chain that we have out there in terms of Rinkaby blockchain, which is helping us to kind of do transactions instantaneously. So here, if you see the amount of time it took for you to post your link and request the ethers and it getting credited to your wallet would have been less than 5 to 10 seconds, right? So it is that instant. So proof of authority is much faster, proof of elapsed time is faster, proof of stake is faster, proof of work is not faster, because here every individual node has to kind of do a certain mathematical computations to achieve that, right? So this is just a brief introduction to consensus, and these are the different types of algorithms we have. When we start writing our code, when we start doing hands-on sessions, and tomorrow we'll kind of see how a couple of these algorithms are used and things like that. So let's have a quick brief about Ethereum platform. So Ethereum is something that we're going to use extensively tomorrow and day after for our hands-on. It's basically an open source blockchain platform which helps us to build and deploy blockchain applications. So the question that might arise is Bitcoin and Ethereum same? They're not exactly same, but they kind of work around the same principles of blockchain. Bitcoin is a use case of blockchain, whereas Ethereum is a platform which helps developers like us to deploy blockchain applications out there, right? So that's what Ethereum is all about. Ethereum also brought in the concept of smart contracts. Smart contracts are a piece of program, a piece of code which runs on a blockchain network to do a certain tasks. So we'll see how this actually practically happens a bit later. You can kind of understand smart contracts are nothing but functions which has a certain code that's running inside a function. That function is running on top of a blockchain network. So this can be a quick representation of what a smart contract can do. Let's take an example that we have two parties, one who is kind of trying to rent a property and one who is trying to one is the owner of the property and one is trying to rent the property. So now, if it is on a blockchain network where they want to kind of automate the whole transaction in terms of the money that needs to be paid as a deposit, the agreement that needs to be generated between both the parties, and how do we choose which parties actually eligible to be able to rent this particular property. So all those conditions can be put into a function, and anyone who is requesting to rent the property needs to meet those conditions first before the things can happen, right? So it's more of an automation that can run on top of a blockchain. So smart contracts helps us to do a lot of tasks faster and quicker without deploying the whole blockchain by itself. It kind of helps us to write small bits of code functions and deploy on existing blockchains and then see outputs along with that, right? So we're going to deploy and build different types of smart contracts to try to understand the languages that is required for scripting or running smart contracts, platforms and editors. We're going to discuss all of that tomorrow and day after and things. So before we wind up today's session, we'll quickly have a brief understanding of the blockchain architectures that we have. Yesterday we spoke about use case in IoT space, we have spoken about a use case in health records, we've spoken about use case in supply chain. Today we'll talk about a similar use case in land records. So I think now we have a fair understanding of what blockchain is, which is nothing but a database stored across multiple computers. And what are the capabilities it has? It has a transparency. It provides transparency. It provides security to the data. It also provides mutability of data and decentralization as a general, right? So when we're talking about a use case, the property records, it's basically a scenario of capturing the state of a property in terms of ownership from one owner to another owner in a blockchain which is tamper proof and which is digital in nature, so that if someone tomorrow wants to claim ownership of the property can easily be verified on a blockchain network. Also, if someone wants to buy a property from someone, can easily verify that if the person who is selling the property actually owns it or no, right? So property records on blockchain can kind of solve these issues. Today in India, where we as a country kind of face issues in terms of when we're buying property, everyone is scared of taking decisions in terms of buying lands slightly outside the city outskirts and things like that. They kind of do a lot of verification and things like that. If all these records government puts up on a blockchain, it kind of becomes easier for anyone to have a transparency of records, who has owned this land from what time period to what time period, and who is currently the owner of the property. If I am buying it, I can easily go ahead and get it verified, right? So few of the state governments are already started working on this space, and they're kind of time stamping all these records into a blockchain. So what exactly will happen is, like, any change in the ownership of the property needs to be mapped as a data transaction within the blockchain, and the process of the transaction will remain very same as how the transaction happened on a Bitcoin network. It will not change anything from that, right? So that's how land records can actually be used in a blockchain scenario. Similarly, we'll talk about a more generalized scenario. Let's talk about digital credentials on a blockchain, right? A digital credential can be a land record, it can be an academic credential, it can be a government credential or a government ID that you have, it can be a certificate that's been issued to you for, say, a skilling workshop like this, right? It can be any of these credentials. But tomorrow, the moment you look for an opportunity, be it a job, be it an internship, be it a exchange program or a higher education that you're applying for, the first and foremost thing the opportunity provider is going to do with you is kind of go ahead and do a background verification on all the skill claims that you do, right? If you're telling that you're an engineering graduate, you're telling that you have skills in, say, blockchain, so the first thing they're going to do is they're going to go ahead and do a background verification and try to understand what is the authenticity of the credentials that you're providing. And the conventional thing that we have today, if Li2 or thingQbator is kind of issuing you a certificate for, say, this particular blockchain workshop, and tomorrow you are claiming that certificate for an internship that you are applying for, they have to kind of reach out to thingQbator, they have to reach out to Li2, kind of verify that this particular student has actually gone through this workshop or not, right? That's what the conventional method of verification of credential works. But the moment you put a credential on a blockchain, what will happen is, like, you can take your all the data. Suppose student X has completed the blockchain workshop on so and so date. Take that whole data, convert that into a hash string, and store that hash string on a blockchain, right? And tomorrow that student goes to a particular organization for looking for an internship, can just share the hash string and tell that you can get this verified on this particular blockchain network, where the verifying authority just enters all the data like the student name, program name, date, and creates a new hash string. The new hash will be matched with the existing hash that is there on the blockchain. And if they match with each other, the record is verified. If they don't match with each other, the record is not verified. Now, what is the interesting thing here is, we are not storing the whole data or the whole certificate of the individual onto a blockchain. We are just storing a simple hash of the data. So in this way, the privacy of the individual is saved. Individual can just have a junk public key that he can use to kind of showcase all his skills and badges stored onto the blockchain. So he doesn't have to reveal his identity to do that. If he doesn't even have to reveal his contact information to do that. It's just a simple hash string which can be only verified by someone who has the actual information to create a new hash. right? So digital credentials is one of the major spaces where blockchain will be used in the future, and there are a couple of platforms which are already doing this. I'm myself currently involved in one project where we are building the next digital credential platform for India. So these are a few things in terms of use case that we have. So today, just to give a quick recap, we discussed about a few usages of blockchain, where to use blockchain, where not to use blockchain. We discussed on key concepts like node, a block, mining, how mining happens, what is immutability of data, what are the functions of the Merkel tree to store data in efficient manner, also to help the immutability of data, preserve the immutability of data. How do we do a transaction in a simple blockchain? How a Bitcoin transaction looks like. We also had a brief overview of the Ethereum platform. We set up our MetaMask wallet and got some free ethers in it. Others who are facing issues, you can send your queries. I'll be trying to solve them just after the session now. And also then post that we discussed about few of the architectures like the land records or property records on a blockchain, or how a digital credential can work on a blockchain, right? So there's a few things that we have discussed today. Tomorrow, to take it forward, what we're going to do, we're going to start running some hands-on. We'll start doing some transactions and see how an actual Bitcoin or a blockchain transaction can work. We'll try to set up networks. We'll try to create some small codes and create our own private blockchain networks and communicate within that, right? So there's a few things that we're going to start doing from tomorrow, and then day after we'll talk about smart contracts. How do we write and deploy functions on existing public blockchain networks like the thingQbator that we have used today in MetaMask or the mainnet. So these are the few things that is there in pipeline for tomorrow and day after. So hope to see you all tomorrow and day after, and we'll start get hands-on. So before you come tomorrow, please have a MetaMask set up, get some ethers into that using the Recovery Pocket. Please have Python installed on your machine, and also the Go Ethereum installed on your machine. So there are a few things that we're going to use tomorrow, and editor that we'll be using for writing our code. Right. So there's a few things that you need to have installed on your machine before we start our session tomorrow. Okay. Thank you. If you have any queries that you want to ask, and we have a few minutes, you can share those over the chat, and I'll start answering those there. Thank you.